Hi everyone, today we're looking at 4.3, Proving Trig Identities. So the first thing we want to talk about is what is an identity. So it's a mathematical statement that is true for all values of the variable for which both sides of the equation are defined. Okay, basically an identity are two equivalent expressions. So just algebraically, if we look at this, 2 times x minus 3 is the same thing as 2x minus 6. So that means that this is an identity. Okay, these two things are interchangeable depending on the situation and which expression will suit us the best. So what we're going to do in a moment is we're going to take a look at these trig identities. So what are these trig equivalent expressions? And we're going to use them to prove that an expression or an equation is true. Meaning that we're going to have both sides of an equation here. We're going to take the more complicated side and we're going to try and simplify it using these expressions of equivalence to make it look exactly like the simpler side, or more simple side. Okay, so take a moment, pause the video, and you want to copy down these trig identities. So all of these are equivalent statements. So depending on the situation and which would be more beneficial, you could say, for instance, cosecant, or you could say 1 over sine, and you will not have changed the value of the expression. So let's try and use some of these to prove that these two sides of this equation are actually showing the exact same thing. So the first thing you want to do is identify the more complicated side. Well, clearly it has to be the left because that has two expressions and the right side only has one. So we're trying to, this is our goal, the opposite side of the equation. We want to make cosine tangent look like sine. So we're going to use those trig identities, those equivalents from the slide before, and we're going to try and swap out maybe a cosine, maybe a tangent. We're going to replace it with an equivalent that will allow me to simplify the left side of the equation. Well, tangent, I saw that I can change that into a sine over a cosine. Okay, if we just flip back for a second. Tangent equals sine over cosine. So I can replace the tangent with sine over cosine, always bringing down the other side of the equation. And I haven't actually changed the value here because tangent is the same thing as sine over cosine. I'm just writing it in a different form. But this form is now allowing me to cross-cancel these cosines, which I couldn't have done before when it was written as a tangent. And that leaves me with just a sine theta on the left, and that's equal to the sine theta that was originally on the right. And I have now just proved that cosine of tangent actually does equal sine. So you need to show this last step. You need to actually show that the left side simplified down to be a sine and that the right side equals a sine like it originally did. Okay, we're showing every step of the work here, every equivalent, if we're canceling things out, because we already know what the answer is. We already know that the answer is supposed to be sine theta. So really the point of these problems is I'm looking at your work. We'll try another one. So I think that a fraction on the right side is much more complicated than just a secant of theta. So I'm going to bring down my secant theta. And I would again like to turn my tangent into sine over cosine. So The method that I like to go with, and this is not by any means a scientific method, I like to try and turn everything into terms of sine and cosine as much as I possibly can, because those are the most common, and they can be used across all of the trig functions. So I'm going to take this tangent and I'm going to change that to a sine over cosine. Now remember, that's just the numerator of the problem, so there's still a sine of theta in the bottom. Okay, well typically when I have a complex fraction, which is a fraction in a fraction here, I like to multiply by the reciprocal. So we do keep change to multiplication, and then we flip. So this is originally sine over 1. I'm now going to multiply by 1 over sine. And by doing that, I can again cross cancel. So I'm left with 1 over cosine. And if we refer back to our identities, 1 over cosine is the same thing as secant. Okay, thereby proving that both sides of the equation are equivalent. Again, I cannot stress how important it is that you show every single step of work, every equivalent that you're making, every cancellation. That's the only way to get full credit on these problems. Okay, one that's more difficult here. I would say that the left side would be what I want to work on. Okay, typically when you have a problem like this, I say go ahead and distribute. So cosine tangent minus cosine secant. Now we can only work on one side of the equation. So once you choose the left, you have to stick to the left. If for some reason that's not working out, go back to the very beginning, start over, and you could choose the other side, but then you can't work the left. Okay, so using my own personal rule of thumb, I'm going to try and turn everything I possibly can into sines and cosines. So that means this tangent, once again, I'm going to make sine over cosine. And secant is the same thing as 1 over cosine. I can do a lot of cross-canceling here. Cosines cancel, and those cosines cancel. So I'm left with sine of theta minus 1, which, whoops, it's supposed to be a minus, which is what I was trying to prove on the right side. Okay, therefore I have just proved this identity as well. Now, in addition to those basic trig identities, we have something called the Pythagorean identities. So I'm going to take a moment and derive how we get these Pythagorean identities. Okay, so imagine that reference triangle in the first quadrant like we've been using. And if this was my theta, okay, this would be opposite, this would be adjacent, and this is hypotenuse. Okay, so what would we use, what property would we use to find any of those missing side lengths? We would use Pythagorean theorem, okay, which is a squared plus b squared equals c squared. So that comes from your adjacent side squared plus your opposite side squared, and that equals your hypotenuse squared. Now, we also were able to relate opposite, adjacent, and hypotenuse to quadrantals. So if you remember, the opposite side was the y, adjacent was x, and hypotenuse was r. So I could switch out those values here. Okay, adjacent is x, opposite is y, and the hypotenuse always had a value of 1. So that's how we arrive at x squared plus y squared equals 1. Okay, now, on the unit circle, when we did sine, cosine, tangent, things like that, okay, so cosine, for instance, we know that's adjacent over hypotenuse. But when we related it to x, y, and r, cosine was x over r, or x over 1, okay, which is how we get to this equivalent that cosine equals x. And the same idea for sine. Okay, sine is opposite over hypotenuse. Relating it to x, y, and r, we get y over 1, which brings me simply to sine equals y. So in this Pythagorean theorem here that I've created, I could now swap out the x and y for sine and cosine. Okay, and this brings me to my first and my original Pythagorean identity. Okay, so we could rearrange it, it doesn't matter. Sine squared theta plus cosine squared theta equals 1. If I rearrange this, I can get two more equivalents, two more identities. So I could subtract sine squared, and I could say cosine squared equals 1 minus sine squared. Okay, I could also do the opposite. I could subtract cosine so this one identity has 3 versions, just depending on the value that you're trying to replace. So pause your video for a moment and just copy down these 3 equations that I've put in boxes. Those are 3 more trig identity formulas. If you're keeping a formula sheet, it might be a good idea. We're now going to take this original one and we're going to derive the other 2 sets. So I can take this whole equation, and what if I divided it by sine? Sine squared, really. So sine squared over sine squared plus cosine squared over sine squared equals 1 over sine squared. Now, the basic identities that we saw a few minutes back, you can square, cube to the 4th power any of those identities, and the property will still hold true. So sine squared over sine squared equals 1. Cosine squared over sine squared, well, that's going back to the basic of cosine over sine. And cosine over sine equals cotangent. So if we're squaring these, cosine squared over sine squared would be cotangent squared. And 1 over sine squared would be cosecant squared. So this is the first in set 2. And again, just like we did in the last one, we could just rearrange these and get 2 more equations. So if I subtracted cotangent to the other side, I would have 1 equals cosecant squared minus cotangent squared. Or I could subtract 1 to the other side and have cotangent squared equals cosecant squared minus 1. So again, pause your video, add these 3 equations to your formula sheet. And now we'll do the last one. So dividing all of this by cosine squared. Okay, and applying our properties. Sine squared over cosine squared is tangent squared. This is 1. Whoops, it's plus, not equals. And this is secant squared. Okay, so that's the first in our third set. And then again, rearrange to get our other equations. Okay, now I won't hold you responsible for how we came up with these 3 sets of equations, but you do have to be able to apply these 3 sets of equations into problems. Okay, so let's look at a few more problems that maybe now involve Pythagorean identities. Whoops. All right, so let's try this one, example 5. All right, so I have 2 terms on the left side. That's very clearly the more complicated side. So I'm going to work on that. Now, these obviously aren't like terms, but I see that there's a cotangent squared here. And cotangent squared was in one of my Pythagorean identities. Now, sine was not, okay? While you can take your identities and square them or cube them, you can't take the Pythagoreans and just say that sine plus cosine equals 1, okay? The values have to be squared. So what I see over here is that there's a GCF of sine. So I'm going to factor that out. And I'm left with 1 plus cotangent squared on the inside. Looking at my identities, 1 plus cotangent squared is the same thing as cosecant. So this right here is a Pythagorean. And I'm going to switch that out. So instead of having 1 plus cotangent squared, I'm going to have a cosecant squared. So always remember what you're trying to get. I'm trying to get a cosecant. Well, sine is the same thing as 1 over cosecant. And if I write it that way, I can cross cancel this on the bottom with one from the squareds. And that would leave me with just a single cosecant, which is what it's supposed to equal on the opposite side. Okay, and I've therefore proven that this identity is true. Okay, looking at the problem, trying to decide which side I want to work on. Now they both have 2 terms, Addition, however, can sometimes be more complicated than multiplication. So I'm going to work on the left. So tangent, I could say, is sine over cosine. And cotangent is cosine over sine. Well, anytime you want to add two fractions together, you need a common denominator. So I'm going to multiply this first fraction top and bottom by a sine, and this second fraction by a cosine. So multiplying this out, I have sine squared over sine cosine, and I have cosine squared over sine cosine. Now I can add these two fractions together, so sine squared plus cosine squared. Okay, the numerator here is a Pythagorean identity. Sine squared plus cosine squared is the same thing as 1. So I'm going to change that out. Remember, I'm trying to simplify here so that I can get a secant cosecant. Okay, so where did I leave off? 1 over cosine, or 1 over sine cosine equals secant cosecant. All right, I just need a little bit more room. Now, the same way that you can multiply fractions and put them together, we can split them apart. So 1 over sine cosine is the same thing as 1 over sine times 1 over cosine. Okay, that's not an identity that I used here. That's just like a property of multiplying fractions. By splitting them apart, I can now switch them to their reciprocal. So 1 over sine is cosecant, and 1 over cosine is secant. Well, we know that multiplication, the order can be changed. So I did prove that the left side equals secant cosecant. Okay, now it's very important to show every single step in your work that I showed in this problem. So showing the common denominator, multiplying them together, putting the fraction together. Do not skip steps in your work. Remember, the work is what's being graded because we already know what the answer is supposed to be. It's supposed to be secant cosecant. Last one. So remember, you cannot work both sides of the equation, which means you cannot cross multiply. So pick a side. Doesn't really matter in this case. So I'm just going to work the left side. So I have 1 plus a cosine. Well, I'm thinking back to my Pythagorean identities, and they all had a 1 plus somewhere incorporated in them. But remember, I said that the identities for Pythagorean don't hold true unless the values are squared. Okay, one of the versions was that I didn't have a 1 plus cosine, but there was a 1 and a cosine squared involved in it. Okay, so if we're thinking about that, we'll just do it off to the side here. So I have sine squared plus cosine squared equals 1. I could also have cosine squared equals 1 minus sine squared, or sine squared equals 1 minus cosine squared. Well, this 1 minus cosine squared, it's similar to what I have. I have a 1 plus cosine. So along the same ideas as the last problem where we multiplied to get a common denominator, we can also multiply top and bottom of the fraction that we have by something if we're trying to change, say, this 1 plus cosine, perhaps into a Pythagorean identity. So think difference of squares. What would you multiply to a 1 plus cosine to get it to look like a 1 minus cosine squared? Well, 1 plus cosine times a 1 minus cosine. Now, please make this very clear. I did not use 1 minus cosine here because it was in the other fraction. As far as I'm concerned, the other side of this fraction doesn't currently exist. I did not cross multiply. I used 1 minus cosine because that was the factor. When I FOIL this numerator, I'm going to get 1 minus cosine plus cosine minus cosine squared. So that is the factor that's going to leave me with 1 minus cosine squared in the numerator that I need, because that's a Pythagorean identity. Okay, I was trying to create a Pythagorean identity in the top, so I chose a factor that I knew when I distributed that, it would leave me with 1 minus cosine. So I did not use the other side of the fraction and cross multiply because it's still here. I have not touched the right side. So 1 minus cosine squared, looking at these identities I have off to the right, it's the same thing as sine squared. Whoops, I have more than that in the bottom. I have 1 minus cosine. Can't forget to multiply that to the bottom as well. Okay, I can cancel one of those signs in the top with the one that's on the bottom. So that leaves me with a sine in the numerator and a 1 minus cosine in the denominator, which is what I was trying to have and match to the right side of the equation.